Hi folks, this is my lecture on electrochemistry, or as I sometimes like to call it, the devious scheme to bend electrons to our will chemistry, because it all has to do with redox, or reduction and oxidation. Right, here we have a beaker with a little bit of copper sulfate solution in it, and here we have some zinc metal strips. What we have is one of the zinc metal strips is a very nice silvery color. Do you see the pretty silvery color? Silver. And when you dip it in here, and you wait just a little while, it begins to change colors. And you can see that it begins to change colors when I pull it out. And you can see it is now darker. And what you've got on the outside of this zinc is a thin layer of copper that has been precipitated and deposited onto the zinc strip. We have studied this before, and in fact we have looked at it in terms of oxidation reduction, and here I've got one that I did a little while ago, and you can see that there's actually all this copper formed on the zinc strip, and it's kind of poofy and brown, and it's very interesting. And so what we're going to talk about is what the heck is going on and how to make it serve us. So here's a picture. Here's a picture of that very same reaction between a zinc strip being dipped into a copper sulfate solution. And these are the reactants, the zinc and the copper sulfate. And here we've got our products. We've got copper, which is the brown crusty stuff that has formed on the surface of the zinc strip. And the other thing that you'll notice is that the solution is less blue now, which is because copper sulfate is blue, and when you start replacing the copper with zinc, you end up with zinc sulfate, which is not blue. So you can see two color changes going on from the silver to the black and the blue to the colorless, and so that should indicate that there's a reaction going on. And here's what the reaction is. You've got solid zinc metal in a solution of copper ions, and you end up with zinc ions and copper metal. And when we've studied this kind of thing before, this is a substitution reaction and also an oxidation reduction reaction, which you can tell because the metals are changing from, this one is changing from its elemental state with an oxidation number of 0 to an ionic state with a number of a charge of 2+, and this one with a charge of 2+ is changing to an oxidation number of 0. So the oxidation numbers are changing from 0 to 2+, and from 2+ to 0, and what that means is that electrons are moving. And the electrons that the zinc has are hopping off and hopping onto the copper ions to form copper and leaving zinc high and dry without his electrons. And the reason that we, and here's a cooler picture. Do you see the brown fuzziness of the copper forming on here as opposed to the black? And the reason that it comes out black is apparently sometimes metal powders don't look the way solid metal does. Like gold particles are red. I think my artists might know that. So let's look at, let's look at this. Where is it? Here we go. We have the activity series, and this is what we've studied before in terms of why the zinc is being replaced with the copper, and we think of it in terms of this activity series, and we're going to get a little bit more complicated with it in a little while. But in the activity series, what you have is a list of metals that can kick out other metals in order to become the compound, or to become the ion. So this is the most reactive metal that you've got, which is lithium. It has a tendency to replace any metals that it comes in contact with, the ions, by ditching its electron and becoming the ion and forcing that electron onto the other metal. So you basically got them in order of reactivity, with the very reactive metals at the top. And as you go down, there's zinc. Zinc is not super duper reactive, but it's pretty reactive. And below zinc, you've got some iron, and you've got some nickel, and you've got some lead, and then you start getting into the noble metals. The noble metals start with copper, And your noble metals are metals that you would tend to use for jewelry, etc., because they have a tendency not to react with anything that comes their way. Copper turns green, though. You say, yeah, but it takes a little while. It doesn't do it like this. And then you've got silver. Silver turns black, though. Yeah, but it lasts longer than the copper does. And then you've got platinum and gold, which gold doesn't tarnish now, does it? So gold has a high tendency to want to be in its metallic state, whereas the dudes at the top here want to be in their ionic state. And that's the way that we've been thinking about this, the activity series of metals. That's why you get your zinc being replaced with copper. We've got nice little fuzzy bits of copper here. I can even shake them off. That's great. Flum, 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 flum. Which means that I've got more reactant space on that zinc available to react. So then this is how we want to think of it now. We know that those electrons are moving from one metal to the other. They're moving from one substance to another. And the reason that they do that is because the electrons are happier on more stable situations. And you can measure the energy in a quantitative fashion as to how much they want to do that. And so you can go, and on this list, what we've got is, this is a list of standard reduction potentials. Now, the word potential, the way that they're using the word potential here, is basically the word for voltage. They're saying that there is a voltage related to these electrons moving. And voltage in the study of electricity is how much energy does each electron have in it, basically. So this is the standard reduction. Reduction being gain of electrons is reduction. Loss of electrons is oxidation. If you remember that, Leo, L-E-O, loss of electrons, oxidation. Leo the lion says grr. Gain of electrons is reduction. Grr, G-E-R. So this is a list of reductions. So you can see that, well, what happens when I reduce fluorine or cram 2 electrons onto fluorine? Well, you end up with fluoride. And you can see on this list you've got your voltage here, your potential here, your EMF, which is your electromotive force. That's what the little E stands for here. So your E for that is 2.87 volts. And what that indicates is if it's a positive number, that means that that's a spontaneous reaction. If your E is positive, it's spontaneous. If your E is negative, it does not like doing what you're trying to make it do. And this is the most positive one that I'm aware of, which should make sense, because if you think about fluorine, it really wants to gain some dang electrons. So it's a lot happier in terms of being fluoride, and so that's a very spontaneous reaction. And the energy of jumping onto that fluorine is 2.87. You got a little bit, you've got gold here, we've got cobalt above you, but you've got gold. One thing that we know about gold is that gold really likes to be gold and not so much gold ions. And so you'll see also that it's quite spontaneous, 1.50 volts, quite spontaneous for gold ions to jam some electrons back on and turn into gold. Chlorine, the same thing. Bromine, the same thing. You'll see a lot of really reactive sort of fellows cramming electrons on here. As you get lower and lower, you're getting less and less spontaneous. There's less energy associated with the reduction of metal ions, or reduction of your halogens here, gaining electrons. And so this is just a list of, well, how exciting is it to be reduced? You get down towards the bottom and you end up with, for example, sodium. If you think about sodium's situation, sodium ions are really excited about being sodium ions. They don't want to become sodium metal again. That's one thing that we observe about sodium metal, is that it's sort of explosive when it reacts with stuff. So it's not going to be super spontaneous for sodium ions to cram the electron back on. In fact, it's quite non-spontaneous. You'll see that this is a negative value of voltage here. And there's not that many that are much more badly off than sodium, but you've got lithium way down at the bottom here. Lithium really doesn't want to cram an electron on, and so you've got a electromotive force, a voltage, a potential of negative 3.05. So this is basically our previous list flipped upside down and measured. So this is a list of reductions and it's flipped over and measured. So one thing that's neat about these electrons is that we can enslave them, because you don't have to take your zinc and put it in the copper sulfate solution in order to get those electrons to jump on and jump off. Because what I want you to think about here is, here's our theoretical zinc strip in our copper sulfate solution. The zinc strip, this is got zinc metal, which has got electrons that are going to hop off of the zinc. And once those electrons have hopped off of the zinc metal is no longer a solid sort of thing. It dissolves in the water as it becomes an ion. So the zinc metal strip, as it's losing its electrons, is going to degrade and go away. And the ions of zinc are going to go into solution. These two electrons, which have just come off of this atom of zinc, are going to find a new home in one of the copper ions that is in solution. So one of these copper ions is going to hop onto the metal strip and join up with these two electrons and form copper. And so what you can see happening is the kind of floofy bits of copper forming on the surface of the metal, because that's where the electrons are that are coming off the zinc. So the zinc is corroding and the copper is plating onto the strip. Now, these electrons have got a certain voltage to them, and the voltage that they have is going to be based off of that list that we were just looking at. No, not that list. Nope. What list was it? Oh, it was the PDF. It's going to be based off of this list here, because what you can see is you've got zinc, and when you reduce zinc and you cram electrons onto zinc, which is not what we're doing, that requires negative 0.76 volts. And when you've got copper ions, which in this case we are doing copper 2 ions and we're adding 2 electrons, when you've got copper 2 ions and you're forming copper metal, that gives you a voltage of 0.34. So what you do is you flip the zinc voltage, because we're not reducing the zinc, we're oxidizing the zinc. So you got 0.76 positive volts for flipping the zinc around. You flip the reaction, you flip the negative sign. 0.76 positives and the 0.34 positives for the copper, and you add those together and you get 1.1 volts total. So you've got electrons jumping off of this zinc and onto this copper with an energy of 1.1 volts for each electron that goes. That's cool. And our devious scheme for bending the electrons to our will involves making them cross a wire. And this is how you do that. And this is what electrochemistry is all about. Come here. All right. So here what we've done is, instead of allowing the electrons to hop directly from the zinc onto the copper, we have forced them to take a path along a wire between the zinc and the copper solution. So here's what's happening in this thing. This is called a galvanic cell, which was named after Luigi Galvani. Sometimes it's also called a voltaic cell, which is named after Alessandro Volta, two Italian dudes who were really apparently into electricity. And we're messing around with this stuff. And in this galvanic cell, we've got our zinc and we've got our copper sulfate solution, but the zinc is not in the copper sulfate solution. The zinc is separated from the copper sulfate solution by a wire. And you've actually, at the end of the wire, you've attached a solid piece of copper to begin with to function as the electrode to dip into the copper sulfate so that the electricity can conduct. So what you've got going on is you've got this zinc, electrons hopping off of the zinc atoms and forming zinc ions, which hop into the solution here. The electrons run up and across the wire, this is a voltmeter that will register the fact that electrons are going by. And the electrons run across this wire, down this wire, and onto this copper. And now this copper electrode has the electrons that the copper ions are waiting for. The copper ions will then hop on to this copper electrode, increasing the mass of the copper that you have on the electrode. And they themselves are reduced. So the copper is reduced on this end, and the zinc, which loses its electrons, is oxidized on this end. And so what this has done is this has separated the two halves of the reaction that we were doing in a single vessel into two vessels. So what we've got here is you're going to end up with a zinc sulfate solution. Here you've got sulfate in here because maybe you put in sulfuric acid or something. And you've got a copper sulfate solution on this side. Another thing that's really important to remember is that if you're taking a whole bunch of electrons from this zinc and cramming it into this beaker, you are slowly increasing the negative charge of this beaker. That's not going to be spontaneous for very long unless you make a way for the charge to cancel out. And so a thing that's really important in a galvanic or voltaic, an electrochemical cell of some kind, is you've got to have some sort of charge neutralizing ability. The common one that you'll see is something called a salt bridge, which is just it can be something as simple as a paper towel that's been soaked in salt solution, so that as the negatives accumulate on this side, the negative electrons, some of your negative ions in that salt can move to the left side, or some of your positive ions in the salt will move to your right side. So those salt ions will be moving in order to counteract that negative charge buildup on this side. A salt bridge can do that. If you've purchased some fancy glassware that is dedicated to the study of electrochemistry, you can get like a dual beaker system that has a little whoop section that has something called a porous disc, which is a fancy type of glass that allows ions to pass but not electrons. Okay, whatever. Anyway, there's got to be some method for neutralizing the charge buildup on the reduction side. Reducción. It's an interesting way of spelling reduction. All right, so that's what's happening. Your zinc is hopping off, your copper is hopping on. This electrode is getting smaller over time. It will corrode and go away and disappear. This electrode is gaining mass over time as the copper sulfate solution gets less and less concentrated. One thing that you need to know, this side is the oxidation side, the side where you're losing electrons. This is the reduction side, the side where you're gaining electrons. The name for the side where oxidation happens is called the anode. This is called the anode. This is called the cathode. The name of the side where the reduction happens is called the cathode side. That's really crucial. You get a lot of questions going, which side is the cathode? And if you cannot remember that reduction happens at the cathode, you will not know. There is a fabulous mnemonic device for which I have made you some beautiful pictures. Here we have this side. This is the oxidation side, which is called the anode. And what you need to remember is, I'm an ox. Here's your ox, an ox, anode, oxidation, an ox. He's on this side right here, anode, oxidation. Then we've got me red cat, me red cat. This is a red cat. Reduction happens at the cathode. Red cat, reduction, cathode. You won't forget it. So there you are. There's that. What else do I need to say? So that's the idea. Oh, and then the important thing is, why are we bothering to separate the anode from the cathode? Why can't we just let it go and do its thing how it wants to all by itself in this one little beaker? The reason is that up here on this wire, we can enslave the electrons. You've got a flow of electrons with a voltage across a wire. That's electricity. You can stick a light bulb here. You can stick a light bulb here. You can stick a motor here. You can stick a fan here. This is the original method for making electricity. Alessandro Volta and Luigi Galvani figured this out. And in fact, they're also responsible for a lot of the original research into producing batteries. So this is called a cell, and you may have actually seen batteries that are called, if you read the little print small on the battery, a dry cell or an alkaline cell. That's what they're talking about. They're talking about a cell. This is a cell. This is a galvanic cell, an electrochemical cell. Batteries are basically these, except, well, when you've only got one reaction going on here, you can only get the 1.1 volts out. If you want to get more voltage, or if you want to get more electrons overall, you're going to need to go boom, 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 and have lots of them in a row. You might have a galvanic cell, a galvanic cell, a galvanic cell, a galvanic cell. You might have 10 of them in a row. And therefore, you end up with something that looks like this. This is one of the original batteries. Do you see the stripes? Boom, 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 boom. They set it up to where you would have a stripe of zinc and some basically salty cardboard, salty wet cardboard, and a stripe of copper, and then something that separated them. And then you do it again. Zinc, salty cardboard, copper, zinc, salty cardboard, copper, zinc. So what you've got is a bunch of cells, cell, 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 cell. And that adds those voltages together, which is awesome. And somebody looking at this pile of cells where you're going boom, 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 said, you know what that looks like? That looks like, you know, like when you're at a castle or something and they've got a whole bunch of cannons, like here's a cannon, here's a cannon, here's a cannon, here's a cannon. What do they call that? They call that a battery of cannons. Do you love it? I love it. I think it's great. That's where the name battery comes from. Come on, get small, notes. Okay, okay. All right. So copper ends up winning these electrons, and the reason that copper wins the electrons is because it loves electrons more. Copper is a more stable metal than zinc is, and that's something that we know based on our observations of how copper and zinc behave in the environment. And we've got the table on the back of this notes. We've got a nice table of standard reduction potentials. One thing that's important to know about this table of standard reduction potentials is that it's actually reduction potentials relative to a standard reaction. The standard reaction that they decided to set equal to 0 was the hydrogen reaction, where you take hydrogen ions and reduce them, and they turn into hydrogen gas, and so it bubbles up. And this reaction would take place at the cathode, because at the cathode you've got reduction going on. And they said, you know what? That's the one that we're going to call our standard cathode. And we're going to compare all of the other reactions to that cathode. And we're going to set that one equal to 0 and say, oh, look at that. The tin 4 to tin 2 is 0.15 more volts than that guy. And the iron 3 to iron 2 is 0.77 more volts. So it's all comparative compared to your standard hydrogen cathode here. And so that's kind of a random question that might pop up is, you know, where did you set your scale off of? And that's the hydrogen cathode. All right. Oh, and that's another thing about this list. The other thing about this list is that these are the standard reduction potentials when everything is under standard conditions. And we've learned about standard conditions before. Standard conditions are, and what's important in this case is 1 molar concentration of aqueous solutions. And that's relevant in a lot of these. Here you've got cobalt 3+. You would need a 1 molar solution of cobalt 3+ for you to get the voltage here of 1.82. It would also need to be at 25 degrees Celsius. So somebody carried out all these reactions very carefully, making sure that everything was a 1 molar concentration solution, and that your temperature was at 25 degrees Celsius. So that's under standard conditions, and you might remember that the little circle, here's the little circle, this little circle means under standard conditions. So your typical conditions, where's my, how do I get smaller? Oh, I can drag this over. Here we go. All right. And then I know what you're thinking. You're thinking, well, but what if it's not standard conditions? What are my voltages then? When it's not standard conditions, the voltages will be slightly different, and but it will be based off of the one that you have under standard conditions. So at 1 molar and 25 degrees Celsius, you've got standard conditions. If you don't, then you have to use something that is called the Nernst equation. This is the Nernst equation, and what it's saying here is that the voltage that you're interested in, the voltage at, you know, some different concentration, is equal to, well, your regular voltage minus some number. It might be a slightly positive amount, it might be a slightly negative amount. 0.0591 is based off of like the gas constant and the temperature and the Faraday anyway, it's just they kind of worked out what all those constants divided out to. It's 0.0591. N is the number of moles of electrons that you're transferring. In this case, in this example, we've got 2 moles of electrons because you got 2 electrons coming off the zinc, coming onto the copper. If you're not really sure, you have to go back and have a balanced equation in order to do that. So you have to go and do your half reaction method of balancing an oxidation reduction reaction. Ooh. So 2 here, 0.0591 divided by 2 for this one, times the log of Q. Uh-oh. I don't remember Q. You don't remember Q? Q is from equilibrium. It's calculated exactly the same way that you would calculate K, but what you, instead of putting in the numbers at equilibrium, you put in the numbers that you've got right now. So for this reaction, where is my reaction? So for this reaction, if we had, for example, do I have a pen? Where's my pen? If we had, for example, 2 molar copper instead of 1 molar copper, you can think about this in terms of Le Chatelier's principle to predict what that's going to do to this reaction overall. Is that going to make it more or less spontaneous? So let's contemplate that. Instead of 1 molar, which is standard, I now have 2 molar copper. 2 molar copper is a higher concentration. I've got a higher concentration of reactants. And what that's going to do is it's going to shift it right. So pushing it right means that's going to make it go more. So increasing this is going to increase your E. And so you're going to end up with a voltage that's slightly larger. And the Q for this is going to be calculated in terms of zinc. This is not really writing very well. Zinc divided by copper. That's what your Q is going to look like. Remember that your solids are not counted. And if there was a 2 here, remember that you would be squaring it, right? If there was a 3, you'd be cubing it, etc. The coefficients are important. So that's how you would calculate your Q to stick it into the Nernst equation. So in terms of Le Chatelier's principle, all right, so Henrietta, let's say that you had more products on your reaction. What is that going to do to your Q? Is that going to make it bigger or smaller? Cluck. You're right, it is going to make it bigger. So when you've got more product, that's the top, and when you have a larger Q, you're going to be having a larger number here, and so you're going to be subtracting off a positive value. And so you end up with a smaller voltage. If you think in terms of Le Chatelier's principle, when you have more product, that kicks it left, which sort of makes it less spontaneous, and so you are going to have a lower voltage. When you're dealing with more reactant, when you've got a smaller Q because you've got a larger bottom, what do you suppose that happens then? Cluck. That's right. When you've got a larger bottom, you end up with a number right here that is a smaller number, and so it can be even a negative number. So you've got this minus a negative number, and so that adds together, you get a larger voltage. And if you think of it in terms of Le Chatelier's principle, if you're increasing your reactants, that's going to shift it right, which is going to be more go-y or more spontaneous. Another thing that you might see is they might say, well, what happens if you have a really big electrode? Well, electrodes are solids. You've got a solid zinc electrode here. And if you just increase the amount of solid, if you remember, that doesn't matter because solids don't go into your equilibrium expression. So that is that, and now it is time to go flip over to the back and do questions 1 through 5. So go ahead and pause this and go do them. Here I go to my black pen screen. Come here. Where are you? Nope, that's not it. There it is. All right. And a couple of directions. When you flip the direction and you're flipping it over so that you are making the anode or the oxidation version, make sure that you flip the positives to negatives and the negatives to positives. And one thing that's funny about these is that you never double them, you never triple them. Even if you have in your balanced reaction, you've had to double, for example, your amount of iron in order to make the electrons balance. You don't double the voltage. You just don't do it. Because these voltages are telling you, are talking about how much energy a single electron has. It doesn't matter if you have more of them. It's immaterial. So, question 1, indicate the oxidizing agent, the reducing agent, the species that is being oxidized, the species that is being reduced, the source and the sink of electrons, and the anode or cathode. The source and sink is how I like to think about it in terms of, well, where did we get these from and where are they going? So let us look at these two reactions. We've got silver nitrate and copper reacting to form copper nitrate and silver. And what you can see is we've got a couple of noble metals. We've got silver, which is, if you remember, nobler than copper. And what you end up having is silver getting his way and becoming the solid metal and kicking copper into the nitrate form here, the ionic form. And you've got to go and look at the silver's oxidation numbers. So here, when you have an element, if you remember, the oxidation number for simple elements is always 0. So here it's 0. Here you've got nitrate, which, if you remember, its charge is -1, and so therefore silver ion's charge here is +1. And so what you've got is silver going from +1 to 0. This is a reduction in charge, so this is a gain of electrons. So you're going from a +1, you're putting an electron on that sucker and it's turning into a 0. So this is a gain of electrons is reduction. Here you've got copper, which has an oxidation number of 0, and copper nitrate, which, if you look here, copper has a charge of 2+. That's going from 0 to 2+. That is losing electrons as you get more positive. Loss of electrons is oxidation. So the silver is being oxidized, the copper is being, no, sorry, the silver is being reduced, the copper is being oxidized. And so to answer the question, which one is the agent? If it is being reduced, it is causing the oxidation of the other fellow. So this is the oxidizing agent, the silver nitrate. The reducing agent, if this is being oxidized, then it is causing the reduction of the other fellow. So there's a loss of electrons, oxidation. It is also the reducing agent. The source and sink, where are our electrons coming from? The source of our electrons. The source of the electrons is the copper. So this is our source. And where are the electrons going? Where are they sinking into? What is the sink of our electrons? This is our sink of electrons. So they're coming from the copper, they're going to the silver. In terms of the anode and cathode, you remember anox, red cat. This is being oxidized, so this is the anode. And this is being reduced, so this is the cathode. Bam. Whew. Okay, that's for that one. Because I have talked through the entirety of this one, I'm going to go ahead and leave this one as an exercise for the reader. All right, question 2. But how will we know if it's right? You can do it. I believe in you. Balance the following equation by the half reaction method in acidic solution. This is that really long, tedious thing that we did towards the beginning of the year. It goes something like this. Aluminum goes to aluminum 3+. This is aluminum metal and aluminum ions, and what has happened is 3 electrons have fallen off. So there, that part is balanced. This is the oxidation half. So this is the one that is taking place at the anode, anox. The other one is permanganate, MnO4 minus, yields manganese 2+. Where did the oxygens go? Well, that's okay, don't worry. They were handled by the presence of water. That's okay, don't worry about that. And the water has just introduced some hydrogen, so we've also got some hydrogen ions in here that we weren't aware of. 8 of them. And because of that, that means our charges are sort of funky, so we've got 7 pluses on this side and 2 pluses on this side. That means our electrons, we need some electrons on this side. This is 5 electrons. That will make it so that we have 2 plus on the left and 2 plus on the right. That's good. All right, so these are both now balanced. With 5 electrons and 3 electrons, what this is saying is that every time this reaction goes once, you get 3 out. Every time this reaction goes once, you need 5. That means that this reaction will go 5 times, while this reaction goes 3 times. So in order to put those suckers all together, you've got to multiply and add up, etc. So you've got 5 aluminums and, no, not 3, 24 hydrogens and 3 permanganates and 15 electrons, and that gives us 5 aluminum ions and 15 electrons and 3 manganeses, scooch, and 12 waters. And you can cross out anything that is on both the reactants and products side. That is the use of 15 electrons and the creation of 15 electrons. So this is the balanced reaction in aqueous solution. Bam. Do you remember doing that? Woo. All right. And which of the following is a better oxidizing agent? Also known as which one would be a better cathode? And I like to think of, it really helps me to think of this list of standard reduction potentials as a list of cathodes. This is a really good list of cathodes. This is the best cathode. This one's not quite as good, but it's a pretty good cathode. Then we're getting down to some mediocre cathodes, and these are really lousy cathodes. So, things that are oxidizing agents are things that are reduced. Things that are reduced are cathodes. So what we can look at is this list of cathodes. If we were asked to look for the best reducing agents, we could look at this list flipped upside down and backwards, because whereas this is a really good cathode reaction, this functions as a really good anode. And so if you flip the reaction backwards and flip the list upside down, it's a really great list of anodes. But as it normally comes, it is a really great list of cathodes. So which of the following is a better cathode? Oxidizing agents like to gain electrons. All right, gold ions or silver ions. Which one is a better cathode? Here's gold and here's silver functioning as cathodes, and for gold you get 1.5 volts of excitement out of those electrons. For silver you get 0.8 volts of excitement, so it turns out that gold ions are better at being cathodes, better at being oxidizing agents. All right, tin 4 or tin 2? All right, tin 4, where are you? Tin, tin, tin. Here's tin. 4 gaining 2 electrons to become tin 2. Now this is interesting. In this case, the tin 4 is not going to hop on to the metal because it's still an ion when it's done. I think you can also find the, well, it just might not be on this list. This list is not comprehensive. The comprehensive list is really long. But here we've got tin 4 that's only becoming tin 2. And so you would have to have a, you'd have to have the electrode that you're using. Oh, could be a platinum electrode in this case. And in fact, a lot of these would be required to be platinum electrodes if the product is not actually a solid metal. So for example, fluorine here, you can't really have fluoride function as the electrode itself because that's not a solid that can conduct electricity the way the metals can. Whereas for this reaction, you can have an electrode made out of gold, and the gold will be hopping on to that electrode. So sometimes you have to use a platinum electrode, platinum because platinum is so non-reactive that it can function as an electrode for any of these reactions. Anyway, tin 4, tin 2. Here's tin 4. Here is tin 2. Functioning as a cathode. This guy is better. You can tell he's got 0.15 volts of excitement in his electrons hopping on, and this guy is actually non-spontaneous, a nice little negative 0.14. So tin 4 is a better cathode. Iron 2 or zinc ions. Where's iron 2? Here's iron 3 becoming iron 2 as a cathode, but that's not what we want. We want, here we go. Here's iron 2. And here is zinc. Here's zinc. Yeah, here's zinc. All right, so who's better? The top guy. He is a better cathode. Negative 0.44 versus negative 0.76. So even those are negative, this is less negative, so iron 2 is better. Oh, the first one. All right, sodium ions or water. Water is interesting because water can function. Here, water is functioning as a cathode. It's negative, so it's not a spontaneously great cathode, but it can be a cathode. And versus sodium ions. Sodium ions, here's sodium ions. And sodium ions can function as a cathode, but they're even worse as a cathode. They're negative 2.71 versus negative 0.83, so water is a better cathode than sodium ions are. One thing that's neat that we're going to talk about in my next lecture is that water can serve both as the cathode in a negative fashion, and you can also see, here he is, up here. If you flipped this around backwards and gave a negative 1.23 volts, you could have the water serving as the anode as well. That is the electrolysis of water. Dun, dun, dun. All right, 3, 4. For the galvanic cell at the left, this guy here, write the balanced half reactions and the balanced net ionic reaction and calculate the cell potential. All right, what do we got? We've got some tin. What tin do we have? Tin. Oh, I should have said here. 4 and 5 go together, and apparently this is tin 2. There we go. This is tin 2. You need to know that. This is tin 2 becoming tin, and no, this is tin becoming tin 2, and silver ions becoming silver. Now here's a tip that is just sort of a qualitative tip. I have never seen an official drawing of an electrochemical cell that has the anode and cathode drawn backwards. It is so customary to draw them where the anode is on the left, the electrons move to the right, and the cathode is on the right. It's so customary to do that I have not actually ever seen an official drawing of a galvanic cell drawn the other way. Now, you can draw them the other way. You can draw the cathode on the left if you want to. But it is a pretty good assumption that if you see an official drawing of an electrochemical cell, it's going to have the anode on the left. The electrons are going to move that way. So that is a tip, and that might save you a little bit of time on the AP exam. You might want to check, but that's a good first approximation. All right, tin and silver. All right, let's look up at the reactions that we've got available to us. Tin 2. Tin 2, here's tin 2. We already talked about him a second ago. Tin 2, SN2 plus. 2 electrons gives us SN. That is one of our options. Tin, 10 electrons, and tin. And that gives us negative 0.14 volts equals our electromotive force or whatever at standard conditions. And the other reaction that we've got to think about is silver. Silver, 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 silver. It's up here. Silver. All right, that's silver ions plus 1 electron gives us some silver metal, and our electromotive force, our cell potential for that guy, half cell potential, I guess is only half the cell, is 0.80 volts. All right, now the way that they're written on the list seems to sort of imply that both of them are being reduced. That is not the case. Is that the case? No. One of these has to be flipped backwards, because right now what we've got is 2 cathodes, and you can't do that. So which one of these is going to be flipped backwards in our galvanic cell in order for it to go spontaneously? Well, we could flip this one backwards and make it positive, or we could flip this one backwards and make it negative. That's going to give us either an electromotive force of 0.94 volts or negative 0.94 volts. Frankly, since we know that they have to be positive in order to be spontaneous, we're flipping this guy. So we're flipping the tin. So in order to make the net ionic reaction, we've got to flip our tin so that we end up with tin hopping off and giving us tin ions and sending 2 electrons up across that wire. So there's that, and then we need to join those 2 together to make our reaction. You may notice this is 2 electrons, this is 1 electron, so that means that this has to go twice. So you've got 2 silver ions and a tin, and 2 electrons gives us tin. No. Doop, doop, doop. Do I have a black eraser? No, I don't. Okay. There we go. Gives us some, what does it give us? It gives us some silver metal, and it gives us some tin ions and 2 electrons. You cross those out. And that is your net ionic equation. The way that you join those together is you go, all right, negative 14 volts is flipped, so that gives us positive 14 volts. So 0.14 plus 0.80 is 0.94 volts. That's your standard cell potential for this electrochemical cell. And if you noticed, I know that you were tempted to double this 0.8 because you doubled the reaction. No doubling. No doubling. Do not double the voltage, because the voltage is talking about just individual electron voltages, not the overall deal. So overall, you're going to get a voltage off that voltmeter that you've got stuck on that thing. When you read it, it's going to say 0.94 volts, ma'am. And that is the voltage of those electrons going across this wire. What would happen qualitatively and quantitatively in the cell at the left if the tin perchlorate were increased to 2 molar? All right, so what we've got is we've got some tin immersed in, to begin with, a solution of tin chlorate, and silver immersed in a solution of silver. Doesn't say. We need silver something. Let's make it silver nitrate because that's real normal and soluble. So we are increasing the concentration of the tin chlorate to 2 molar. If you do that, take a look at this reaction. We are increasing our tin ions. Now, if you remember at standard conditions you got 0.94 volts. At standard conditions, it's 1 molar. So we have increased the concentration of a product. If you increase the concentration of a product, that, according to Le Chatelier's principle, is going to shift it back to the left, which is going to make it less spontaneous. And so I expect that our voltage is not going to be 0.94 anymore. It's going to be slightly less excited. It's going to be something less than 0.94. So that's the qualitative description. The quantitative is using the Nernst equation, which is this super duper exciting equation here. Your standard minus some little bit. N, how many electrons are we transferring? That's 2. Here they are, 2 electrons right there. Bam, 2. Times log of Q. And for Q, you've got the concentration of your products to their exponent, which is this guy, no exponent but the 1, over the concentration of your reactants to their exponent, which is squared in this case. And the concentration of your tin you have just increased to 2 molar. Concentration of your silver is staying at 1. And so, there we go. We've got this going on, so that's 0.94 minus all that. And you stick that in your handy dandy calculator and look at the answers that you've already calculated on the back of your paper, Mrs. Gunlock. And you know what that gives you? That gives you a voltage at non-standard conditions of 0.93 volts. Why, that's less, isn't it? Yes. All right, that is number 5. All right, this is really long. I'm going to do another lecture, so come back and see lecture 2.